Okay, let's get started. Hi, everyone, and thanks for joining our webcast today. My name is Lisa Milkava, and I am the Communications Director over here at Capsulate. A couple quick housekeeping notes before we get started. Please do feel free to ask questions in the box provided. Dino's going to try to get to as many as he can during the time that we have available. And also, a recording of the webinar will be available for download on our site next week. We'll let you know as soon as it's up, and we also will provide a link to Dino's slides as well. And now I'd like to introduce today's presenter, Dino Daizovi. He's the co-founder and CTO over here at Capsulate. He'll be sharing a bit more about his experience during the webinar, but quick background. Dino's a well-known researcher and innovator in the cybersecurity community with more than a decade of experience, and he's also a regular speaker at InfoSec conferences around the world. And today he's going to be sharing an encore of his very popular session he presented just last week at KubeCon in Austin, How to Prevent Attacks at Scale on Cloud-Native Environments. Dino?
All right. Thank you, Lisa. Thank you, everyone, for attending. I'm going to talk about preventing attacks at scale. This is the work by myself and Trevor Tissio, our infrastructure lead here at Capsulate. So first, talk a little bit more about my background. I think a lot of people are familiar with my research experience, but not as familiar with some of the hands-on stuff I've done over my career. So I consider myself a breaker turned builder. I spent the early part of my career especially focusing on learning how to break security and how to make it better through breaking it. Starting at the IDAR Red Team at San Diego National Labs, at State, Monsanto, and also authored books including iOS Hacker's Handbook, Mac Hacker's Handbook, and the Art of Software Security Testing, and frequently presented at Black Hat on how to understand attack techniques. But throughout the later stages of my career, I've actually focused on building security in. And my first exposure to services-oriented environments was as Director of Security at Two Sigma Investments, and I spent the last 3 years as a staff security engineer and a mobile security lead at Square, building their mobile security team and platform. And now I'm taking a lot of that to Capsulate, where we're focused on building the industry's only real-time attack disruption platform purpose-built for cloud-native environments. And I'll tell you a little bit more about how we think about that in this presentation. But I wanted to make sure that it's clear that I'm not talking about our product here. I'm talking about the general problem space and how you can build a lot of these sort of architectures quickly and relatively easily. So one of the biggest problems facing our industry is the cybersecurity skills shortage. And we talk a lot about this, and there's a lot of different solutions to it, but the magnitude of the problem is simply staggering. It's been estimated that we have a shortage of roughly 2 million cybersecurity professionals by 2019. Over half of organizations experience delays of over 6 months to find a qualified candidate. And even among those, 84% of organizations believe that half or fewer of applicants for the open security jobs are qualified. And this is also made even worse given that we need cybersecurity jobs to grow at 3x the rate versus IT jobs overall. So the need for jobs are increasing, and it's becoming more difficult to find the people to fill them. And cybersecurity is not unique in these problems. And historically, another area that has had similar issue has been data center operations and infrastructure operations. And there was a similar problem where they initially were scaling with bodies versus scaling with software. A relatively recent study of the number of servers per employee across companies found that while the average company had roughly 0.1 or 0.4 servers per employee, Facebook and Google had way more. Facebook having 30 to 1, Google having 50 to 1. And that's a significant increase in scale. And how did they do that? Well, the primary way they did that is by treating operations like a software problem, because software scales so much better than any manual process. And they clearly did this to great effect and were able to achieve larger impacts because of this. So there's a kind of a meme about software is eating the world, but it's hard to understand what this really means. And what it really means is just that the idea of software, when it takes over a new business or it goes into a new area, because it can scale so much more efficiently, it tends to dominate. So if you just look at kind of the titans of today, they're all companies that apply kind of software mentality to domains that were not previously run with software. And it's been said that sort of DevOps is software eating ops. And what's happening now is software is also eating security. So here's what I want people to kind of take away from this talk and kind of understand. The CTO of Amazon is famous for saying, you build it, you run it. And that was their mentality for how, rather than having separate infrastructure teams that were responsible for keeping services up, the engineering teams themselves were responsible for this. And this is because they had the most power to change the code to actually make the software more reliable. And if they didn't feel that pain, they were less connected to the quality of that software. And a similar mentality, this is a mentality that has pervaded DevOps, SRE, whatever you want to call it, but it's pretty much the dominant way that online software is developed these days. This mentality is also spreading over to security now. And the way we can phrase this is, if you built it, you help secure it. And you're ultimately responsible for securing it. The security teams help build the infrastructure and provide the resources, but they cannot scale to be ultimately responsible for the security of the massive footprints of an organization, especially when product teams and application development teams are given a lot of autonomy, which is crucial for the organization to be able to be agile and move quickly. But what's important about this is that being able to apply a lot of these sort of automated security solutions doesn't require a PhD in defense against the dark arts. What we've seen from a lot of breaches is that the tactics are not always as sophisticated as you'd think. So it doesn't require super deep expertise in order to understand this. And we're going to talk about how to build a continuous security pipeline in cloud-native environments using pretty off-the-shelf tools, mostly cloud APIs that are very easy to get running in Amazon, Azure, or GCP. And also talk about how the principles of SRE and DevOps can apply to security. So this is what I want everyone to think about as we're diving deeper into how we do this. So let's go a little bit on the background here. The inspirations for this come from three areas primarily. First, my experience at Square building their mobile security system, where we focused on server-driven detection of tampered app or mobile devices, of millions of devices running thousands of firmware versions, and how to build a sort of automatic low-latency pipeline to detect this. Similar approach was undertaken at Google using data mining for security. And I have links so you can see the presentations behind all this. What they found in their experience was that purely statistical and applying machine learning to the data had actually poor results for them, because just there's a lot of features and still not a lot of context. And primarily that in machine learning, 80% true positive rate is a paper-worthy research result. However, a 20% false positive rate in security is horrible. And at scale, it basically crushes the system. So that can have pretty bad effects when it's employed naively. And what they found is that a rule-based expert system had much better results, and that's what they ended up going with for this system. A more recent approach was presented by Netflix about how to employ eBPF for security monitoring. And what I think is most important about with this presentation are their requirements that drove their decision, because Netflix is a highly cloud-enabled company, massive footprint in AWS, and you can see a lot of the template for how they do things is very indicative of how most people are going to need to apply security as they move to the cloud and are able to scale up in the cloud like they have. So their requirements were they needed to be event-driven. They needed it to push the data for analysis rather than having to pull it from all the systems, especially because when you're scaling up and scaling down, it's very difficult to keep a consistent list of the servers that are available. They needed to be lightweight and not interfere with the workload. And they also needed kernel level inspection. They wanted to see what was happening inside the kernel to detect even kernel level attacks. So what they settled on were using custom probes using eBPF on Linux trace events. And I'll dig a little deeper into what this actually means and how we can use techniques like this. Overall, I'm going to focus on 3 of the 5 factors to secure systems. So Ryan McGeehan, also known as Magoo, coined these 5 factors as an approach to secure online services infrastructure and kind of break down what needs to happen. And especially focusing on a holistic approach versus just patch every vulnerability, which becomes very difficult at scale to do in real time. So first, focus on response, that you'll be able to respond to the threat as it occurs. Once you identify a threat, you need evidence. You need to trace the threat steps forward and backward and have good visibility into what happened so that you can identify the scope of the activity and improve the system going forward. Third, you also need to focus on containment and mitigation, that threats will have limited impact. Things that we're not going to talk about too much today, because I think it's been covered a lot in the industry and it's kind of a more established steps in this process, are prevention. The threat isn't likely to occur. This is namely patching and making sure that attacks aren't possible for known tactics. And the fifth, elimination, which he describes as mitigation through innovation. This is ways to mitigate an entire class of attack or class of vulnerabilities. So at least on the software security side, we focus a lot on the last two. But one of the unique things about online serving environments is there's a lot more opportunity for the top three because the attacks always occur on your territory. It's not actually your attack surface isn't a product that is running on someone else's infrastructure. We are building systems that are our infrastructure. So when there's activity of someone identifying vulnerabilities, it's often visible in this infrastructure. And that's a unique opportunity that we should take fullest advantage of. So first, we also need to figure out what we're going to call this thing, this discipline of applying these factors to an online environment. Some people have called it SecDevOps. Others are preferring DevSecOps. Some people are trying to call it DevOpsSec, or traditionally they just call it SecOps. I think permuting these three syllables also muddies the idea, because security should be part of all of it, not in between two phases or ahead of one or the other. So what we like is just calling it continuous security. And we think of this as the counterpart to continuous delivery, which is the real technology that people are trying to get out of cloud era and cloud native technologies. Being able to be agile and deliver features quickly and seamlessly. And what we need is we need security to integrate into every piece of this pipeline. So what we call continuous security is primarily a software-driven pipeline to securing systems. You approach this like a software problem where you build a feedback cycle, and this feedback cycle is driven by security monitoring and attack testing. Like any piece of software that you launch in production, testing for load is critical, and for security, we need to do this for attack and make sure that we're testing against real scenarios as possible. The results of this will prioritize our prevention efforts. Like a software optimization problem, we'll focus on the bottlenecks and we'll optimize our efforts towards those bottlenecks to get the most impact for our time versus spending all of our time defending against an avenue that is really difficult to exploit when there are very easy avenues to exploit for an attacker that we have paid little attention to. And the workflow often revolves around a focus on reducing the false positives and negatives iteratively. Once you set up the system to generate the signals, you can iterate and improve the quality of that signal as you go along. And one of the most interesting things about this is that it doesn't actually require having a dedicated security team. And just like there are many organizations that are breached and compromised that don't have security teams, we need to make sure that we can defend our infrastructure without a security team in place. And the best way for, I think, practitioners and organizations of all sizes to go about this is to work backwards from public breach postmortems. One of my favorite places to start is a page called the Blockchain Graveyard, because blockchain companies and cryptocurrency companies are pretty unique in their openness and transparency on breaches that occur. And this is an invaluable resource for other security practitioners to identify sort of these traces of attack for a high impact breach that are often company ending, and see how it happened, what could be done to prevent or mitigate those attacks. And one of the interesting takeaways from the statistics that this is also from Magoo that he found is that the largest cause of corporate death in the blockchain graveyard were server breaches. And so that's what we're going to focus on today. So let's work backwards from what these look like. So today, because this is a talk that was given at KubeCon, we're going to focus on Kubernetes environments. And we're going to talk about the vulnerabilities that are most likely to be exploited in those serving environments. And these are remote code and remote command execution vulnerabilities. These have turned out to be startlingly prevalent in open source software that are used as internal components in a large amount of software running the internet today. So some of the kind of well-known names behind these vulnerabilities are Shellshock, Image Tragic, there's Apache Struts vulnerability that affected Equifax, and a massive array of vulnerabilities involving Java deserialization that have been referred to as mad gadget vulnerabilities. But one of the common aspects of all of these, all these vulnerabilities, especially as they affect Unix servers, which basically means Linux servers at this point, is that these are all remote command execution. These are not memory corruption. These are not difficult to exploit. You don't need to bypass ASLR and worry about a low amount of reliability or crashing the server. These are remote, 100% reliable, and let you directly run shell commands, often with a level of privilege against the remote site. And these are typically as discoverable remotely as SQL injection, where you can determine whether a site is vulnerable by sending a piece of input and seeing the server give you an error in response or cause a delay. So that's definitely an area that we're going to focus on because these are kind of the most likely game over vulnerabilities to occur in cloud environments. Other bad things that can happen in containers, someone can load SSH into a container or provide some other quote-unquote backdoor. I call it a quote-unquote backdoor because it could be a malicious backdoor inserted into software, or it could just be something that an engineer creates in order to help them debug what's going on in production, which may be against policy because it also puts the environment at risk. This can also identify potentially risky practices such as hot patching a container in production, which is not replicatable, so it's just not a good practice. But this is also a similar activity to what it looked like to have someone backdooring a running container. So we're going to focus on how to detect all sorts of these activities. So let's go through a hypothetical data breach scenario and trace through its steps, especially as it applies to a Kubernetes infrastructure, Kubernetes environment. So first, an attacker is going to discover that an exposed service is vulnerable to an RCE vulnerability. They will probe, they will look around, they might even be able to just detect that you're running a piece of software and already have the crafted input that will run commands. Because they can do that remotely without really having to engage with your environment. However, the next step, once they exploit that RCE vulnerability and start executing shell commands in that container, they are now in your environment in unfamiliar territory. So they're going to have to look around. They're going to have to kind of explore a little bit in order to find what they need to execute their objectives. Usually along that path, they're going to work on escalating privileges within the cluster. And today, with Kubernetes, there are a couple avenues where this is commonly possible. First is that role-based access control in Kubernetes has not been enabled by default in many versions and many ways to deploy it. So a weak RBAC policy often allows containers that are running in Kubernetes to have increased privileges, so they might be able to launch another privileged container. And once they have launched a privileged container, they can access the underlying node operating system or do other things to maintain persistence. The other avenue is looking at other internal services running in the cluster because the segmentation between workloads is often not ideal in many environments, especially because the infrastructure to provide this is still really under development. So one example of this is the service called Tiller, which is the server-side counterpart to the Helm package manager that is popular for installing packages in Kubernetes clusters. This service doesn't require authentication or authorization, and you can access it across namespaces and install software. So once you have access to a container in the cluster, this is usually available and it's game over. Through either of these methods, an attacker is going to work on establishing privileged persistence in the cluster and then move laterally within that cluster to achieve their objectives. One of the notable aspects of especially these attacks in server environments compared to desktops is that while it might be acceptable to observe an attacker for 60 days in a desktop environment in order to gather more intelligence on their tools, tactics, and procedures, in a server environment, often you don't have that much time. The time from initial access to company-ending breach can be much, much shorter, and in some cases, some published scenarios on the blockchain graveyard, as low as 3 hours. So this is something where we need to design our defenses accordingly, because this entire data breach scenario may be in the span of a small number of hours. The vulnerability we're going to talk about to explain this a little better is Shellshock. Shellshock is a fun one because it was around in Bash for a very long time, I think roughly 15 years. It was exposed through a variety of vectors over the web, over in DHCP clients. And my favorite part about it is that it doesn't require any special tools to exploit, and the crafted input to trigger the vulnerability is relatively readable to people who haven't done a lot of penetration testing or other sort of like vulnerability research. So that's what we're going to talk about and demonstrate. So let's show a quick demo of how to exploit this against a container running in Kubernetes. All right, so to demonstrate this, I've set up a port forward from my laptop to the cluster, and the container running Apache that's vulnerable to this is running in that cluster. So the dynamically assigned port is 37417. There's an Apache instance running there, and it's running also a test CGI. So test CGI was included in older versions of Apache just to demonstrate the CGI interface, and notably it's a shell script running in Bash. So this actually exposes the server to the Shellshock vulnerability because it takes how CGI works is a lot of variables from the HTTP headers are translated to environment variables, and then the program is run. So by having a shell script that is run either directly or indirectly through CGI, the attacker is able to craft environment variables that get sent to that program. And the underlying basis of the Shellshock vulnerability is in how Bash parses environment variables to identify function definitions that it needs to import into a subshell. So to demonstrate this, we're going to craft the content type header and include a command that will be run. And the syntax that we're creating is defining a function without a name, but the bug is also in that Bash allows you to define a function and then append commands. So when the Bash subshell parses this environment variable, it will define an empty name function, but also execute that command. So we're going to try and execute the ID command to get our user IDs. But the challenge is that we don't actually see the output. So we need a way to figure out that the server is vulnerable, and kind of a common trick for this is to use a sleep. We can see that based on the thing pausing for 5 seconds, we probably have control. We can verify this by doing another sleep and seeing if it changes. 1, 1000, 2, 1000. Clearly we have ability to execute commands here. And so the way that we'll exploit this is by injecting a bit of Bash command line to execute an interactive shell to a remote TCP socket. So what we're doing here is we're launching interactive shell, and we are using a pseudo device that Bash supports called dev TCP that allows you to redirect to a socket and also allows us to read in from that socket as well. So let's flip over to another window, and we can see what the attacker sees on that side. So here is the attacker with a listening netcat. So we're going to SSH to a jump box somewhere in the cloud, which we can create on demand. So this IP address isn't in any threat intel because it's malicious as of 2 seconds ago. And we're going to set up a listening netcat. And then we'll see once the shell connects from that command in the other window, we now have interactive access to the host. From the shell, we can see that we're an unprivileged user, which is the best practice for running in containers. However, the state in this cluster, we don't have role-based access control enabled because it is the default installation from an open source tool. So that means that you have full access to the cluster even from the unprivileged shell. And so there's a variety of things an attacker can do from here. So in order to evaluate your own cluster and see what's possible from there, I recommend trying out our Shellshock vulnerable container. You can get that from the Docker Hub and exploit Shellshock on your own Kubernetes cluster. I just have to warn you that don't expose its web port outside of the cluster because it's clearly vulnerable and will give everyone remote access to it. I recommend launching it in its own dedicated namespace and using a kubectl port forward to actually get access to it. And that way you can experiment with it without putting the cluster at a lot of risk. And this gives you a great view to see what an attacker would see from that infrastructure. So now that we have an attacker has access to a container, to a shell inside a container, how are they going to do Proto Distillation? The notable thing I keep in mind here is that while there's a lot of focus on the security boundary to the local node, either via the Linux kernel or and like security hardening of the container, or via like a virtualization boundary running around a container, I found that the most serious vulnerabilities are always related to the Kubernetes API and the Kubernetes environment. So the attacker can exploit the weak RBAC even if they're running inside a highly secured container with a hypervisor, because the element that needs to be applied that I think is more new, so people have a harder time identifying that it's a weak point and also how to address it, are these cluster level security mechanisms. So RBAC or Helm will give you full access. For more information on how to do this, I have a turbo talk that I gave at Kubernetes NYC that you can see at this YouTube link and watch me compromise a cluster in 5 minutes using these techniques. So now let's work backwards from the breach and see what we need to do. So what we want to do in order to identify activity like this is monitor all process execution within containers, and especially for shells. We also need to monitor all the network connections within the cluster, because there are several activities that we want to be able to identify, trace back, and also ideally alert on and respond to in real time. First, any pods communicating with the Kubernetes API servers. This is rare. Not all pods need this ability. And so, whereas you can turn this off by default, usually most people don't, so you're going to actually want to identify this activity. And especially sensitive services such as the tiller service, any pod communicating with it, you'll want to be able to identify that activity. And focus, for network connections, focus on even attempted but unsuccessful connections. So even if you have a production environment that has strict egress filtering, software that is attempting to get out is a pretty valuable signal. So let's talk about how we can build a continuous security pipeline to identify this activity and respond automatically. So our strategy is first we're going to gain visibility into activity on this infrastructure. Second, we need to make sure we can enable investigation to all of this past activity and give us an opportunity to implement detection to generate alerts. I found that a lot of this is done really well by kind of augmenting known alerts with your own, so that you want to enrich things that are unique to your environment and hand tune them, because this is also sort of this cycle of identifying the activity, detecting it, and crafting the responses is sort of where human time is best applied. And also implementing the automated response to these alerts so that this activity is automatically responded to across potentially arbitrary scale, and then iterate through this process. How we're going to go about implementing this, kind of a little more concretely, is we're going to start with the events. And we need to gather events from a variety of data sources that are security relevant. So one way, first thing to start with is logs that are already being generated, system logs, application logs. These are definitely a crucial ingredient, but it's also important to implement sensors at various points of the infrastructure to gather more pointed data. And this is also something that the security team should have more control over, to choose which data is acquired for their own analysis. And these events are analyzed to generate alerts for humans and other automated systems to respond to. And ideally, this happens off the node. Because the node is usually going to be the first entity to be compromised, this analysis, if it's done externally, is a lot more resilient and difficult to interfere with when an attacker is breaking in. These alerts should be responded to automatically wherever possible, and this is one of the key ingredients making it necessary to scale. And this should be your default option. One of the benefits of modern infrastructure, including containers and orchestration and auto-scaling, is that there's a lot more statelessness built into the fabric of how we deploy services. So what that means is that a default option of restarting a container, restarting a node, actually goes a long way and can be relatively low impact if you go about it by, for instance, draining the node in Kubernetes or doing other options. And it makes it and you can also drain traffic from it. It's actually a pretty good response, and you can even do things like acquire more data from a node when there's some level of suspicious activity. And how kind of the human security team interacts with this is they're working on the pipeline by monitoring alerts, doing manual investigation, tuning the sensors to gather kind of more or different data, balancing performance and visibility, and developing and maintaining the automation for the responses. This is one of the key ingredients to scaling a continuous security team, because focusing on automation means that you don't have many tiers of humans looking through alerts. You have software doing the repetitive jobs and having humans focus on the novel and new. And it makes work a lot more fun and interesting too. So for the architecture that we're going to talk about today, it's a simple proof of concept. This is something that is very similar to IoT telemetry analysis systems that are presented usually as a blog post or a white paper from the cloud providers. And we've adapted it to a security use case. So this is not something that's super complicated. So we're going to start with a auto-scaling Kubernetes cluster of AWS instances. And these are going to send their events into Elasticsearch via Kinesis Firehose. Kinesis Firehose is a managed data streaming service from Amazon that auto-scales up and down and provides a simple delivery stream that can also call out to Lambda for data transformation, and has a variety of destinations, including S3 buckets, Redshift for further analysis, or we're going to use Elasticsearch so that we can use Kibana as an interactive interface for human analysts to look through what happened. And we're going to use the ability to transform data in Lambda from Firehose as a hook to generate alerts and also to enrich the events with other data. The nice thing about doing this in Lambda is that it has a much further reduced attack surface, because there's no one has access to the underlying host except for Amazon. And if attackers have access at that level, it's all game over for you anyway. So it means it's one less resource that the security team has to worry about. And the scripts in Lambda are going to generate alerts on a SQS queue that are responded to by elements, by software running in the cluster that has access to Kubernetes APIs and can initiate responses where necessary. One of the nice things about using kind of a cloud architecture for this is all of this can run in separate cloud accounts from the rest of the infrastructure. So this could be infrastructure that is solely accessed by the security team for greater isolation, and that means that if there's a compromise of other cloud credentials, this monitoring infrastructure is not also compromised at the same time. So I'm going to dive a little deeper into how to hook in Firehose and Lambda for detection. So the Firehose takes streaming events from a variety of data sources and is able to perform transformation via call out to Lambda, and that's what we're going to do. And then the destination configured for Firehose is an Elasticsearch cluster. And so for this example that we set up, creating this was all possible in a few minutes through the Amazon console. It's click, click, click. This is actually pretty simple and not actually the hard part. So the event data that's of interest to us is we want to look at environment monitoring. In bare metal environments and on-prem, kind of the net flow from network equipment was traditionally considered the ground truth. In a cloud environment, that's basically the ground truth is provided by the API access, the API audit logs for the cloud. So in Amazon, that's CloudTrail, and the VPC flow logs, so we can see what's actually happening on the network. However, one of the challenges with modern environments such as Kubernetes is that the VPC flow logs may not give you the full scope of activity. You may just see, you don't get that visibility into which containers are running on a host and which processes are in those containers. So just knowing that a particular IP address performs some action when the workload is dynamically scheduled, it's not as useful. You can also feed in logs from Ingress. Ingress is the HTTP router built into Kubernetes, so you can use that to identify HTTP requests across the entire cluster. Feed those as events for network monitoring. But what we're going to drive a little deeper on is system monitoring, so we can get this process level activity and even deeper. There's 5 choices we're going to talk about today, starting with Capsulate, the Capsulate Sensor, which is a to-be open source project that we have sponsored and will be releasing very soon. Go Audit is a lightweight pure Go client to the Linux Audit subsystem, written at Slack. Go BPF, also written in Go, an interface to the Linux eBPF facilities as part of the iAdvisor project. Facebook-sponsored OS Query, a popular system to execute queries across your infrastructure and gather data. And final option is Sysdig, which is commonly used for system visibility in Linux. So what we're going to try to accomplish with any of these systems is identify which process, container, or pod performed a particular suspicious action. So even if we're getting an alert that a particular IP address did something suspicious, we need to be able to drill deeper in to see what was behind that IP address that did this. And then what else did it do? Was it performing networking within the same pod? One of the challenges in Kubernetes is that 2 containers in the same pod may be communicating. And when they do, that's over a loopback interface, very difficult to get visibility into that activity. And also when they're communicating within the same cluster. And also we want to be able to dive deeper into why did this process perform a suspicious action? Where did that process come from? Who executed it? Did a human run a shell in the container, or did Nginx spawn a shell? If it did, that's very strange. And in a particular cell session, what commands were executed? We want to have the ability to query all of this after the fact with high fidelity of information, and then most importantly, a low performance impact. Of these agents, there's various trade-offs, and we're going to go from the design considerations from Netflix's presentation as well, because we found them to be actually what we looked at as well. The first is that whether the system is event-driven, and is pushing data versus pulling. In a distributed system, if you're relying on pulling across the environment, often there's the list of systems that are active become out of date, and this is also relatively inefficient because you can't pull really quickly. Whereas something that's pushing events and is streaming events in architecture is a lot more, has a lot lower performance overhead and lower latency to any response. The monitoring also must be lightweight. And what I mean by lightweight is it must not impact the workload negatively. I'm going to talk a little bit about how Audit, the Audit subsystem in Linux is particularly impactful on your workload, especially when the system is under load. The third criteria is whether it performs kernel level inspection, whether we can look at what the kernel functions that are executing within the kernel to identify deeper behavior, so we can identify even kernel exploits, and whether the system is kernel version independent. So of these choices, because these are the criteria that we use to design Capsulate, clearly we hit all of those, but there's different trade-offs for the other systems as well. So notably, any system based on Linux Audit, including Go Audit and OS Query, we don't really consider lightweight because of its ability to block the workload and cause performance overhead to go parabolic. All the systems based on Audit and system call monitoring aren't able to identify kernel level activity. And also kernel version independence is important at scale because you may have many different versions of the kernel. So Capsulate is pure userland, so it doesn't actually depend on the kernel version. Anything using Audit is also kernel version independent. Sysdig, I say, is kind of on the cusp because it loads a kernel module, so it has to recompile the kernel module for a new kernel that it doesn't have a pre-built module for. So there is some increased access it needs to your system in order to load if you're running a new kernel that it hasn't seen before or a slightly different distribution. So those are the trade-offs. Clearly, we're a little biased. But what I wanted to drill into was the performance impact of Linux Audit versus Linux tracing. So for a given sample workload, which was just a kernel compile that was configured to be massively parallel as a stress test, and monitoring a small number of system calls, fork, exec, exit, and open. So we wanted to identify process activity and all file system activity and get an audit of all that activity. What is the impact of the workload? So with Capsulate Sensor, the workload is, workload time increases from 2 minutes to 2 minutes and 23 seconds. Sysdig increases to 2 minutes and 29 seconds. Go Audit, unfortunately, because of the Audit subsystem, it hits a bottleneck when the backlog limit is hit and the workload is actually paused. And this causes the time to go up to 6 minutes. So this is a pretty common concern about using Audit in production, especially with system call level auditing, because it's pretty easy to hit this bottleneck. So this is why we feel that using systems based on Linux tracing are much higher performance and a much safer bet for production than using Linux Audit. So this is what we built into Capsulate Sensor. It's a lightweight container-aware system monitoring agent. No kernel module required, so it doesn't mean you have to violate the vendor-signed kernels. It's 100% pure Go, not even using CGO, and it's a single static binary, no installation required. We'll be opening up the repo for our first alpha release as soon as possible on GitHub, so you can get it and try it out. It's brought to you by the letter alpha, the word Apache, and the number 2.0. So it's still very much in development. We are actively working on it. You can watch the PRs land as we're adding more features and adding more capabilities to the system. So for this proof of concept architecture, showing how we can use this in Kibana, if you're using Capsulate Sensor where we're adding events with container information and all this and process activity, it makes it really easy to search for things like, hey, has anyone run a BusyBox in my Kubernetes cluster? And it'll each event will say which image it came from. You can identify pods that were launched with a BusyBox container, and then you can drill deeper onto what those did by searching for the unique container ID. So as you're using Kibana to further investigate an attack, as an example, You can search for anything running BusyBox, and then you can get the unique container ID, and then search across the cluster, or sorry, search for all activity related to that container ID, and drill deeper. And this workflow is what is helpful to kind of fully understand what happened. But what we really want to do is detect things in real time, or as close to it as possible. I point out that what I'm talking about here using Firehose is not what I'd call real time, because the delay can be up to 60 seconds. It's normally about 10-ish seconds for something to work its way all the way through the system. But when we're developing our incident detection in Lambda, one of the nice things about it is because Lambda supports something as simple as JavaScript, as well as Python and full-on Java, you can increase the sophistication of your attack detection logic incrementally. So you can start with something, just looking for something like a BusyBox container and alerting based on that, or you can start doing increasingly sophisticated state tracking as well. And being in Lambda, you have a reduced attack surface. So I think this is a great place to get started. So running as a Lambda transformation with Firehose, all you have to do is send the same event back, or you can also enrich it with additional data if you want. And anything that is considered worthy of an alert, you can use any Amazon API. So SQS message queues are ideal for pushing alerts, and you can have other systems pulling down from those to respond automatically. The responding to these alerts can be very simple. So if you're pushing a simple JSON payload from Lambda, you can actually take a lot of these actions with just a shell script. So a pod running in Kubernetes that is pulling messages from SQS, you can pull out the pod identifier with JQ, and then just use kubectl delete to delete the pod. And this is a relatively small shell script, and all of a sudden you have the ability to automatically terminate any pod that has been identified as malicious from your logic in Lambda. And this is another area where you can invest a little more into automation and building in this infrastructure. So as you kind of have the architecture laid out, the next steps that really help are increasing the sophistication of this in line with the sophistication of the attacks against it. So start with reproducing any attack that you can via open source security tools. Metasploit framework is great for this, and especially the high profile attacks and like breach scenarios that are published, try to replicate them on your environment so that you can ensure that your continuous security pipeline is able to detect and respond to this. And as you increase the sophistication of the simulated attacks and the attackers performing them, you can increase the sophistication of your pipeline in step. So some popular ways to do this are if you have a bug bounty against your infrastructure already, you should try to use the continuous monitoring pipeline to identify researchers before they submit their report. Because the vulnerabilities need to be identified live against your infrastructure most often, there's an opportunity to detect attack-like activity using the same infrastructure. Hiring a professional penetration tester is also recommended, and you should use this infrastructure to monitor and detect them as they are assessing. And you can choose whether to respond or not, but as you work your way up the ladder, I recommend hiring a professional red team that actively tries not to get caught. You know, this is the real test, because attackers clearly don't like getting caught. A red team that knows how to simulate that style of attacker is invaluable to building a better pipeline and training your team especially. So thank you for your time. I have about 5 minutes left, and if there are any questions, I will get to those.
Thanks so much, Dino. I think we are all set. We did have one question come in that asked about whether or not the architecture that you were describing was real-time, but I know that you did kind of answer that on the fly.
Yeah, that's kind of a common response to this is how real-time is this? And because we're using AWS Firehose, which is a managed service and is meant to be simple to use rather than very low latency, kind of the bound of the response is about a minute. But you'll usually be at the lower end of this, but it's definitely not milliseconds. And for real-time response, you need something that is more sophisticated than what I've talked about here. All right. Well, I'd like to thank everyone for their time.
Great, thank you so much. Thank you everyone for joining. And like I said, we will be sending out the full recording of the webinar as well as Dino's slides coming up next week. And if anyone does have any questions after this is over, please feel free to reach out to us at info@capsulate.com. Thanks so much.